So we are going to start topology, one of the most important course in pure mathematics. So we are going to actually dive into it. Before that, I want to clear and talk about all the concepts of pure mathematics, which are all the heart and core of pure mathematics. So I want to discuss all of that. So the book I will supposed to follow is General Topology by Schaum outline. So we will not only solve this book or everything, we will try to study it and to understand the actual meaning and the actual science or actual wisdom behind all the topology and topological space. So are you ready with that? So I am super excited for that. So first topic of general topology by Schaum outline is sets and elements. So what is sets and elements? Set is none other than is a collection of well-defined collection of well-defined objects, collection of well-defined and distinct objects. So what does mean by distinct? In this definition, I want to say that I have a set in which objects are distinct, but I have a set in which objects are distinct at the same time. The the objects in this set are defined very well. What does it mean by defined very well? It means that, for example, if I say I have a set and in which I have a collection of all the chefs in the world. What does it mean by chefs? It means everyone in this world who cooks something is a chef. Yeah. But if I say I have a collection of chefs who cooks professionally, then you are supposed to or you have to include all the chefs of the world who cooks professionally. Not everyone, because everyone of us can cook something in our entire life, but we are not chefs, because the chefs are they are professional. They are so the collection in this set are distinct and should be non-ambiguous. There should not be any ambiguity in that, whether it is an element of the set or not. So you should be super clear with that, right? So this is a very important definition of the sets, which should be very clear. Okay, so moving to it, sets are generally denoted by capital letters, noted by capitals letters like A, B, X, Y, and etc. Right, and etc. And if these sets are enclosed by the curly brackets, right? Over very important curly brackets, right? If and the objects in these sets are over elements, and these elements are generally denoted by small letters, like A, B, X, Y, and etc. Right? If I have a set, for example, X is equal to A, B, C, and that is all. If I want to say that A is an element of X, or if I want to say that A is an element which belongs to the collection of elements in the set X, then I will write that A belongs to set X. I will write this statement like it. Similarly, if F is any element and I can see that it is not in our set X, then I will write that F is an element which does not belongs to our set X, right? Super important. So our sets are finite or infinite depending upon the number of elements in the set. If I have a set and having only one element called singleton set. If I have a set having only one element, then it is over singleton set. And very, very important thing is that repetition of objects is not allowed. So you should not do not have to repeat elements in this set. Not allowed. So these are all our very, very basic and important information about sets and their elements. If I give you some example of the sets, then very famous and very important of a set of natural numbers which starts from 1, 2, and the series goes on. This is an example of set over set of natural number. Similarly, over set of whole numbers, which is starts from 0, 1, 2, and similarly over set of integers, start including 0, plus minus 1, plus minus 2, and the series goes on. So this is the very important information about sets. Now we move to our next concept, which is very important, like our sets concept, and the topic 2 of our book is subsets and the concept of a super subset. So what is a set? So subset. So subset is a part of set. Part of set. So something not, no, something very close and related to sets is our subsets. Okay? And then subset contains the element of sets. The elements of set, right? And always remember that number of subsets of set is 2 power n, and n is the number of element in it, right? Okay, then if A is a subset of B, means that subset of B means that A is a set and contains the element of B. Then I will write it as A is a subset of B, right? A is a subset of B. Then always remember that B is a superset set of A, because A contains, B contains A, because B contains A. So what does mean by superset of B of A? It means B contains A, right? Is it important? And it is very interesting, right? Very interesting. Each element of set A belongs to B, then it means if X belongs to set X is any element which belongs to the set A, then as A is a subset of B, then it implies that X also belongs to B, right? So B contains A. I have proved it as, right? This is our proof, right? Exactly. Very important. Very interesting. Okay. Then if number of elements in subset is less than number of elements in set, then it is over proper subset, written as, right? It is A is a super subset of B. Sorry, A is a proper subset of B. So this is the most essential and very important information about our subsets, right? So all the sets are subsets of a fixed set. So our next topic is, so what is collection, classes, and spaces? This is the word of classes repeat many times in our book. So it's very important to understand this concept. So always remember that the members of a set are sets themselves. For example, if I want to talk about this set of real numbers, right? It contains over rational numbers, over irrational numbers, over integers, over integers, over whole numbers, and over very important natural numbers. So if I talked about a natural number, which is which belongs to the set of real numbers, but it is also in itself is a set. So have you seen that you can see that natural real number is a set which having the element as an element natural number, but natural number in it is a set, is itself is a set. Similarly, every element of the set of real number is itself is a set. You can see it. Similarly, if I draw a line, which is a straight line, so this straight line is also it also belongs to a set of this straight line contains a lot of points, so it belongs to a set of points, right? I hope you get the idea of that. So we use the class we use class. We use class word for set of sets, right? So class of natural number, so class of natural number, like it belongs to the set of real numbers as well. So I hope. Similarly, the members of a set are sets themselves. For example, each line in a set of lines is a set of points. As I explained earlier. To help clarify this situation, we use the word class, collection, and family. Always remember that if class, collection, and space having same meaning, they all mean that we are talking about a set which belongs to the collection of sets, right? The words subclass, subcollection, and subfamily and me all are on analogous to subset, right? I hope this all are clear to you very well. So our next topic is product set. Product set, very important, very important concept. Yeah. So always remember that product sets written as A cross B, right? We have two sets A and B, and we define their products. So it is that we have two sets and defining a product on it, and this and written as this. And this product of sets are oftentimes called very famous Cartesian product. I hope you are familiar with that product. Okay? It consists of ordered pairs of ordered pairs where ordered pair like this A comma B, where A belongs over set A and B belongs to over set B, right? In A cross B. Remember that I'm talking about A cross B, right? Our next topic is relations. So the simplest explanation you can find of relation is that it is a subset of A cross B. It means that if I have a set 1, 2 containing elements 1 and 2, and if I have a second set which is contain the element 2, 3, then A cross B is 1, 2 and 2, 2, 1, 2, 1, 3, and this is our elements 1, 2, 1, 3, 2, 2, and 2, 3. I should close it. So these are our product of two sets, right? I have, make two, we have two elements in each set, and we have write them in ordered pair form where first element belongs to a first set and the second element of us belongs to a second set, right? So this is our A cross B. Then if I want to write a relation on it, then relation is this. If I take one element or if I take any subset of A cross B, then I can have a relation, right? Is it important? Yeah, it is very interesting. It is also like if you relate, if you relate A to the B, similar to that, and then can we write is then write as A R B. If not, if A is not related to B, if do not have a relation, then written as A is not related to B. Is it very, very interesting? So, relation is a subset of Cartesian product. Simply it is that, right? So, can we write as, so R dash is equal to our subset of A cross B, then R contains ordered pair of A, B, where A is related to B. So this is the very important information about it, right? So, okay, our next topic, before we actually move on, I want to, elaborate one more thing, which is the domain of range. Domain and range of relation. So of relation is that. Okay? So if I have a relation, let's suppose this. I take relation from the above. We have 1, 2 and 2, 2. This is our relation R1, right? Then in this relation, my domain of R is the first element of order pair is 1, 2. And my range is the second element of our order pairs, which is 2 and 2, right? So in order pair, in our A belongs to domain of R, while our B belongs to the range of. Simply is that. Okay. So our next topic is equivalence relation. So equivalence relation roughly satisfies. Always remembers that equivalence relation exists only of. Acha, okay, I am just so it is a relation, a type of relation. First thing, is a type of relation, and then it satisfies three very important topic, very important properties. Three properties. Properties number one is reflexive property. Number two is it satisfies symmetric property. So our third property is symmetric transitive property. If we have a relation and it satisfies over these three specific properties, then we can say that it is our equivalence relation, right? Or can be, for example, I written as that a comma a belongs to our relation, and if I have a comma b belongs to relation, then our b comma a should be in it. I mean, if I have a, b, and b, c belongs to relation, then AC should also belongs to me. So by these three properties, I want to, I want to satisfy these properties. For example, if I have a set, yes, I have a relation R is equal to 1, 1, 2, 2, and 2, 3, 3, 2, that is all. And I want to say, check it whether it is a equivalence relation or not. So how I can check it? I can check it by checking my three specific properties, which is reflexive property, transitive property, and symmetric. So, firstly, we will check our reflexive property. And we can see that in our given relation, reflexive property holds because 1, 1 and 2, 2 is there. Similarly, our second property is symmetric property. Symmetric property also holds because 2, 3 and 3, 2 is also present in our relation. Our last property is transitive property. Transitive property in this relation, we will check for 1, 1 holds, 2, 2 holds. Always remember that as if we have similar elements in an order pair, then over all the three properties, it means holds. So now we check for different elements, right? For 2, 3, we have 3, 2, and 2, 2 is in our relation, right? So our transitive property holds. As all the property hold, then our this relation is our example of our exactly equivalence relation. So now we have examples here. Very important examples. I will recommend you to solve examples on your own firstly, and then see the solution. Okay, right. So prove that A is equal to 2, 3, 4, 5 is not a subset of B, where B is an set where B contains element X such that X is even number. So B is a set of even number. How proof करना? How we that set A is not a subset of set B. We have to show this, right? So as we can easily prove that because 3 and 5 belongs to A, while 3 and 5 does not belongs to the X as, right? So it does not belongs to X. So 3 and 5 does not belongs to set B. It means that this implies that it implies that A is not a subset of B, right? Very simple question, very easy question. Our next question is that if A is a subset of B and B is a subset of A, then prove that, A is a subset of C. So very simple. If A is a subset of B, if A is a subset of B, then let X be any elements belong to A, then as A is a subset of B, this implies that A also belongs to B, right? Then as B is a subset of C, then which implies that X belongs to C, right? This implies that as X belongs to A, then as X belongs to C, then it implies that A is a subset of C. Very simple. Very simple questions. Our next question is that if A is a subset of a null set, then A is equal to empty set. For this question, always remember that we have a hashtag point here that every, in fact, empty set is a subset of every set. Always remember that. It implies that it means empty set is a subset of A, right? And in our question given and as A is a subset of empty set. So from 1 and 2, we can write from 1 and 2, we can write A is equal to 5. As 5 is a subset of A and A is a subset of 5, then A is equal to 5, right? Or next question is that find the power set of the set S is equal to 1, 2, and 3. Always remember that power set of a class of all the subsets. So power set is the class of all the subset. Class of all subset. So in this question, we have asked to find all the subsets of S is equal to 1, 2, 3 indirectly. So first question that comes to our mind is that if anybody has asked us to find all the subset, then first question is that how many subset exist? Then the answer is that 2 power n subset is existed, and 2 here is the number of element in a set X, and in this case we have 3 elements. That means 8 subset exist of the set containing 3 elements. So this power set of S is equal to in our slide I have written that power empty set is a subset of every set. So we write empty set. Every set is a subset of itself. So I have written the whole set S, and single element, singleton set, and over order pairs 1, 2, we have 2, 3, and we have 1, 3, right? How many subsets till now we have? I think so we have that. Exactly, we have 8. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 subset. We have find all the 8 subset of a set S is equal to 1, 2, and 3. So very simple and very easy example. Always remember that the key point is that 2 power n is the number of element exist, number of subsets exist in a set. This is our next example, which involves operation on set. Operations on a set. Operations on a set. Exactly. So over in this question we have U, we have A, we have B, and we have C, right? So in first part we have to find A complement. Always remember that A complement is the set we get after subtracting, yeah, after the difference by U minus A. So a U set is 1 to 9 elements, and so we can write it 1 to 9 minus 1, 2, 3, 4, right? Is it that? Exactly. So means the difference of U and A contain all the elements which is in U but not in A. So first four element have common are common all in both the sets. So the elements that are in U but not A is over exactly 5, 6, 7, 8, and 9. So this is the word complement of A. The second part is to find A intersection C complement. Exactly. So firstly we find A intersection C. So the common part of A and C, where this is our A set and this is our C set. The common part 1, 2, 3, 4 and 3, 4, 5, 6. So you can see 4 is the common element between A and B. So this is our A. So complement of A intersection C, A will be exactly consist of exactly. Also 3 is also common. Sorry, I forget that 3 is also common. I'm sorry. So A union A intersection C complement will be all those elements that it means we have to minus A intersection C. So U minus A intersection. So you have first three elements, first 9 elements, and we have to subtract 3 and 4 from it, and we get 1, 2, 3 and 4 was subtract, and 5, 6, 7, 8, and 9. So this is the complement of A intersection U, A intersection C. So our third step is difference of B and C. So by this I means that elements that are not in B but in C. So this is our set CB and this is our set A. So I think so we have 2, 4, 6, 8 and 3, 4, 5, 6. So I think so 2 is not present and 8. 2 and 8 are the elements that are present in B but not present in C. Right? Is it clear to everybody? Right. Our last example, last part is A union B complement. So firstly we find A union B. We have all those elements present in A and B. So we have 1, 2, we have 3, we have 4, 6, and 8. And now we find its complement. So A union B complement will be AU minus A union B. So we have 1, 2, 3, 4, 5, 6, and 8. So we have minus 3. So we have 3, we have 1, we have 3, we have 4. We got 5, we got 7, and we got 9. So this is the complement of A union B. So in this way, you can easily find anything, right? These are the operations on set. So our next question is prove that De Morgan's law. De Morgan's law. Very simple. De Morgan's law. A union B complement is equal to A complement and U complement. So this is our question, right? So we take our left hand side, and we get A union B complement is implies that X such that X belongs to A union B complement, right? It means that X does not belongs to A union B, right? It implies that X does not belongs to A or X does not belongs to B, right? It implies that X belongs to A complement or X belongs to B complement, right? Implies that X such that X complement A and union B complement. So we have, oh sorry, we should, we should, eh, right? We have to write and here. right? Exactly. So we have intersection. So A intersection B we have. So we have to take this side and prove this side. Very simple, very fascinating, right? Our next example is that A is equal to this, B is equal to this, C is equal to this. We have to find A product B union C. Very easy. Firstly, we find B union C. We have all the elements in B and C. So we have 2, 3, and 4. So take the cross of A, B union C. So we have A, B from A set, and we have 2, 3, and 3. Now we find or take the Cartesian product or the product of two sets, 3 and this, and B comma 2, B comma 3, and B comma 4 is our answer. So very simple. Exactly. Consider the relation R is equal to 1, 1, 2, 2, 2, 3, and 3, 2 in X, which is our set. Determine whether it is reflexive, symmetric, and transitive. So try it yourself firstly, and then watch the rest of the video. Right? So 1, 1 is there. 1, 1 belongs to the relation, right? So reflexive property holds. Firstly, reflexive property holds. Exactly. Okay. 1, 1 holds from relation, but 2 is present in the relation, but 2, 2 is not belongs to relation. So not reflexive, right? Exactly. 2, 3 is there, and 3, 2 is also there. So symmetric property holds, right? Symmetric is there. Thirdly, over 1, 1 is there, 2, 3, 3, 2 is there, 2, 3, and 3, 2 is there, 2, 3, and 3, 2 is there, but 2, 2 is not there, right? 2, 2 belongs to relation, 3, 2 belongs to relation, but 2, 2 does not belongs to relation. That is why, so not transitive, right? So this is our last question. We are done. I hope it helps you a lot. Don't forget to subscribe to our YouTube channel and like, share, and comment. See you in another video. तब तक के लिए